Folks, this one's going to be brutal trying to keep it under 20 minutes, so we're just going to hit it hard and go as quick as we can. We're talking about coordinate geometry, which is a new idea, and we'll just get right into it. This is out of Pearson Text section 6.8 and 6.9, and we're going to be looking at figures in coordinates and using them in proofs. So, remember a while back we worked on a problem that looked like this. We were basically trying to prove the triangle midsegment theorem, and I gave some of you the problem that said look at vertices of a triangle and then prove that the midsegment is parallel to the base, and also that the length of the midsegment is 1/2 the length of the base. So what we did, we plotted the points that it told us to, and then we used the midpoint formula to find the midpoints. For EF it was 2, 4, and you can follow along with the calculations there yourselves, remembering the midpoint formula. And for FG it was 7, 4. So we plotted those midpoints, drew our midsegment, and then looked at the figure, and we realized that the slope of both the midsegment and the base are 0, therefore they must be parallel, and that the length of MN, well, we can just count 1, 2, 3, 4, 5, is half of the 10 units on the base. So we proved the triangle midsegment theorem for that particular triangle. But if you remember at that time, I also gave the honors people a different problem. I said to try and do it with variables, A's and B's and C's, instead of numbers. All right, and there's a reason for this, and I'll talk about that in just a bit. Okay, basically, what we did then is we used again the midsegment or the midpoint formula, only we used it with variables, 2a and 2b, instead of actual numbers. And then we did it again over here. And using the variables, well, we found out 2a plus 0 for FE. All right, there's our x coordinates. So we plugged those in there. And for the y coordinates, we plugged in 2b and 0 right there. And we found that the midpoint of EF was going to be at some point we'd call A comma B, right? Without using numbers, we just derived the formula that said our midpoint was going to be at A comma B. Then we did the same thing for FG using variables, okay? And we found this was going to be at A plus C for our x coordinate and B for our y coordinate. All right, now it looks a little prettier here on the next slide. So, using those values then, we then calculated the slope using the slope formula, right? Change in y, b minus b, over the change in x, and we found that the slope of mn was 0, just like we used the slope formula on EG and found that its slope was 0. Therefore, the two lines were parallel. Then we calculated length using the distance formula. All right, we plugged in for mn the x coordinates, a plus c minus a squared. Then we did the same for the y coordinates within the framework of the distance formula. And what we ended up doing, we end up seeing that these a's cancel out. That turns to a 0. We end up with the square root of c squared, and of course the square of anything squared is just itself. Therefore, we found that the length of mn was c, and it's pretty obvious here the length of GE is from 0 to 2c. It's 2c units long compared to c for the midpoint. So what we've done, we proved that the midsegment was half the length of the base. Here we proved they were parallel. So instead of using actual numbers like we did here, what we did here in the new problem using variables, we proved since a, b, and c can be any number, we proved the theorem is true for any triangle, not just for specific coordinates, all right? That's called a coordinate proof. So there's our vocab word for the day, coordinate proof. Using just variables, if we can prove something true, we know it's true in all cases. Since A, B, and C are totally undefined, they can be any numbers. This can be any triangle. All right? Now, you notice we use a little trick. I used 2A, 2B, and 2C instead of using just plain old A, B, and C. All right? We did that because I knew I was going to be using the midpoint formula. And, of course, the midpoint formula, going back again, involves dividing stuff by 2. So it made it a lot easier to use 2A here and 2B here so that we came up with a midpoint that wasn't a fraction. If I'd have just used A and B, I'd end up with fractions here, and I don't want to mess with that. That's why we use 2A, 2B, 2C instead of just plain old variables. Although we could have. It would just make it harder. All right? This is one of the first challenges in working with coordinate proofs. We got to designate the points in the easiest possible way. So we'll give you a couple examples here. Now, first of all, I'm going to start with coordinate proofs. We don't put any numbers on them. We're just going to use an x-axis and a y-axis and the origin and go from there. Again, all of our points are totally undefined since we're only going to be using variables, no numbers. All right, so here's a little practice example. We got SQRE. It's a square where the side length is 2A and the axes bisect each side. What will that look like? Pause, answer coming in just a second. Here we go. All right, SQRE, side length is 2A, and if the axes bisect both sides, I know the origin must be right in the middle because it's going to cut the sides in half. All right, so anyway, the trick here is that our coordinate, now this will be a little easier to see if I start up here. This means I had to go over A, up A, therefore our coordinates are A, comma A. Over here I went negative A and up A to get point S. Negative A to get down here, and positive A, negative A to get to R. Okay, so that satisfies the definition of the problem, all right? So the length of each side is 2A, and each of the coordinates is listed as such. Okay, try it again here. We now have an isosceles triangle, TRI, where TI is equal to 2A, and the y-axis is a median. Pause, and I will show you what that looks like right away. All right, isosceles triangle. TI, the length is 2A, the y-axis is a median, which means it goes from a vertex to the midpoint of the opposite side, meaning these are congruent. Therefore, I'm at negative A, 0, positive A, 0 for I. Now R, I had to choose another variable because it has nothing to do with A. That's why the B is in there. Okay? Try another one. RECT is a rectangle. Height of A, length of 2B, and the y-axis bisects these two sides. Give it some thought. Here comes your picture. Okay. Height of A. All right, so each of these points goes up. Y-coordinate is A on both of those, meaning it's A units high. And if the length is 2B, with the y-axis bisecting these two sides, I must have negative B, 0 for my R point, and B, 0 for the T point. Okay. One more. Got a kite. You can read along. Pause. Answer coming. That's what that one's going to look like. Okay. All right, you ready for some real proofs? Prove that the diagonals of a parallelogram bisect each other. Well, our first task is to draw ourselves a parallelogram. Now, I've chosen the points. Again, I know I'm going to end up using the midpoint formula, so again, I'm using that 2b, 2c, 2a trick, all right? So we got a point. We're going to start at the origin for one of our vertices, all right? One side, this bottom side, is going to be 2g units, or 2a units long, okay? So I know the other side has to be 2a units long, but it starts at a point that I'm going to call 2b, right? So this would be 2b on my x-axis, and then it's going to be 2a units long, just like this one. So its coordinate, the x-coordinate, is 2a plus 2b. So I'm starting here, adding 2a to get to this x-coordinate point right there, 2a plus 2b. Okay, they are both 2c units high. Okay, and of course I'm picking A, B, and C. They're pretty much random the way we designate them. If you had other letters or other variables, that would be fine also. So I'm just kind of making it up as I go along. It makes sense to me that I would just use A, B, C. Okay, I happen to choose C for the height, A for the length, B for the starting point of the top of that parallelogram. Okay, now where am I going to go with that? We're going to prove that the diagonals bisect each other. So if the diagonals bisect each other, then point H here in the middle has to be the midpoint of both diagonals. So let's find the midpoint. Again, using the midpoint formula for both diagonals, OF and EG. Okay, so for EG, we plug in the coordinates as we laid them out, right? 2a plus 2b would be coming from here, right? Those are the x-coordinates. Divide by 2. The y-coordinates go 0 plus 2c, divide by 2. Simplify that down. We're going to find out that the midpoint of EG is at some point that's going to be called A plus B in the x direction and C in the y direction. All right, now let's do the midpoint of OF. It's a little more complicated because I got an x coordinate of 2a plus 2b, but then at least I get to add 0. Let me change colors here. Okay, they're all annotations. So 2a plus 2b plus 0 gives me my x-coordinate, divide by 2, and my y-coordinate, 2c plus 0, divide by 2. Work out the math. We find the midpoint of OF is A plus B comma C, same as the midpoint of EG. Using only variables, we've proven that the two midpoints are the same point. Therefore, these two segments must bisect each other. And we've done our proof. Okay, try another one. Prove that the midpoint of the hypotenuse of a right triangle is equidistant from all three vertices. Pause, think about it. Here it comes. We'll lay out our triangle this way. Use the origin for the right angle. Point E is at 0, 2B. Point F is at 2A, comma 0. And again, I'm choosing the 2's because I know I'm going to use the midpoint formula. To find point M, I'm going to use the midpoint formula for the hypotenuse EF. So I plug in the x values, which are 0 and 2a. Then the y values, 2b and 0. Divide them both by 2. And we find that the midpoint right there is at A, comma, B. Okay, now we need to use the distance formula to find those three distances because that's really what the question's asking, right? So the distance from E to M, using the distance formula, again, plug in coordinates, 0 from here, A from there for your X values, okay? Your Y values are 2B and B. Simplify it down. We find the distance from E to M is the square root of A squared plus B squared. We can do the same thing for MF. Again, using the M value, A comma B. We plug in the A from the X coordinate here, the X coordinate there, Y coordinate B, 0 from here. Simplify the math. And then do the same thing for MO. And this one's nice because we got zeros for both values at the origin. Simplify them down. What we end up seeing, the distance of all three comes out looking the same. Therefore, we have proven that the midpoint of the hypotenuse of a right triangle is equidistant from all three vertices. That one, and that one. Finally, one more. Trapezoid midsegment theorem. We're going to prove both parts of it. Okay? This one's a little more complicated. So I say lay out a trapezoid just in general. Pick 2A for my point G, origin for another vertex, 2B, 2C, and then 2D, 2C. And again, these can match because they're equally high, right? Because the trapezoid has to have parallel sides. All right? So that's the way I want to specify my variables. I'm going to use the midpoint formula to find point M and point N. You can follow with the math. And we end up finding that the coordinates of the midpoint here, B, comma, C. And over here, this is going to be at A plus D, comma, C. All right? So the trapezoid midsegment theorem that we're trying to prove has two parts. First, the midsegment is parallel to the bases. Therefore, let's check the slope formula. And the slope of EF, slope of MN, slope of GO, all come out to be 0. Again, just using zeros and the variables that we have in place here. All right? If you need to study that, please do so. Pause as much as you need. But we end up finding out that using those coordinates for M and N, plug them into the slope formulas, we're going to find the same slope for both MN, for all three segments, MN, EF, and OG. The second part of the trapezoid midsegment theorem tells us that the length of the midsegment must equal the average of the two bases, or the mean of the two bases. So let's figure out the lengths. Distance formula to find the length of EF. You can follow through. Okay? Distance formula to find the length of GO. And we didn't even have to really do that because I know that the length is just from 0 to 2A, right? But anyway, you see the distance formula going on there. Down here, the length of MN, and it comes out to be this kind of strange thing here. Okay? Actually, I should have erased that D and said it's MN there. But anyway, length of MN is A plus D minus B. When I take the length of EF and GO and average them together, right, 1/2 of the sum, I plug it in, we follow through with the math. You know what? You find that same set of values, A plus D minus B, A plus D minus B. Therefore, we have proven that the midsegment is in fact equal to the average or the mean of the two bases. All right, that's what I got. I hope I kept it short enough. I hope it makes a little sense. We'll play around with this tomorrow.